I'm gonna post this up in a Codeberg repository. I was gonna use GitHub, but literally look at this, dude. What? Wait, what's happening today? Wait, compiling review feed. What? Live updates. Damn. Hello, everyone. Editing 10x Wizard here. What you saw was just the beginning of me programming this mini project, but this mini project took me about stupid enough, I think 3 hours to program, as dumb as it sounds. Yeah, obviously I'm not a 10x engineer because a 10x engineer would not spend that much time on that project. I'm not gonna go ahead and sift through all that footage for your guys' sake in mind. So instead, I'm gonna give you a rough rundown of the mini project. So this is the mini project that I came up with. And this mini project is really good for Leetcode and interviews and understanding algorithms a lot more, especially for people who are trying to take data structures and algorithms. A class of that in college. This gives you a really good head start. And so this project is basically making a randomly generated maze and then solving said maze with a variety of algorithms. I did DFS and BFS because every data structures and algorithms course will do DFS and BFS. But there's other ones too that I would like to do, like A-star, which is really cool. Godot engine uses that, and I may have a project cooking up in Godot. Loki looks like ass though. So how did I make the random maze generator? The first thing we need to discuss before getting into the project is specs. So I'm gonna tell you guys exactly what to do here. This is essentially so you can follow along with me or do the project on your own. It shouldn't take you too long. So the first things first is to make a maze generator. So here it's like a terrible Among Us character. Why is that here? Alright. So first things first is that you need to make the maze generator, correct? So how would we go about that? How can I move this? There we go. So the maze generator, at first, you need to take into account, you need to build the maze. So the maze is going to look like something like this. And then our character is going to be O, and it's going to spawn in this left-hand corner. And the finish line will spawn in the opposite corner. You can make the characters whatever you want, make the walls however you want. For me, I made the walls specifically this character, right? This, you see on your keyboard. And then I made the sideway walls equal to a dash on a keyboard, not underscore, a dash. Correct. And then here you're going to also make it that randomly some spots will be X and others will be spaces. So you're going to have X's and spaces all around. And the character can move diagonally. So this is, to here is fair. So those are the overall rules of making the maze generator. I don't know if I'm going to have a project document. If you guys want one by chance, I could go ahead and link it into the repository. But if you guys don't want it, yeah, just comment down below if you guys want a project document. So this is how you make the maze generator. This is the first part. This is the specs we have for the maze generator, right? Now for the maze solver, we already disclaimed. For the maze solver, we're going to make it that the character can move wherever it wants, like diagonally and such. But it cannot move on the X's. It can only move in spaces, and it cannot move further beyond the boundaries, right? So for the solver, essentially, we have the character, and we're going to make two approaches. Those two approaches being depth first search and breadth for a search. So the best way to explain this is if we have a graph here, right? We're gonna make a little tree, okay? This is gonna be a tree of leaves. These are gonna be leaves. They're known as nodes in computer science. I'm gonna call them leaves for now, right? So breadth first search here essentially goes 1, right? But then it goes here 2, but it'll, instead of going down, it's gonna go back up, and then it's gonna look at another path. So this will be 3. And so now, since we're on this level, then breadth first search would be like, okay, so now I'm gonna look at what this is connected to. 4, 5, and then it'll look at what 3 is connected to, and it'll be 5. Oh, 6, 7. Okay, and then it will find that it's connected to 6, 7. And so if you wanted to search for specifically 5, it would go 1, 2, 3. Why is that 4? It'll go 1, 2, 3, 4, 5. And then this is marked as node 5. And depth first search on the other end. That's why it's called breadth first search. It goes every level. It goes level by level, right? And so if you had something more complicated, like this, right, then it would still go level by level. It would be like, oh, 1, 2, 3, and then since these are connected to each other, it'll look at 3, it'll look at 2, and then it'll look at everything it's connected to, and it'll see 3, but it won't renumber it, essentially. That first search, on the other hand, is going 1, 2, and it goes all the way down 3, and then since it can't connect to anything else, it'll go up to 2 again, then it'll go down here to 4, and then it sees 4 is not connected to something, so it goes to 2. 2 has no more connections, goes back to 1, goes down, goes 5, goes down again, 6, no more connections, and so on. And so overall, okay, cool. Why this is so important is because we're gonna implement these solutions to our character. And so when we do breadth first search, we're gonna make the character is gonna look at this position. I'm gonna mark every position it's gonna look at with L. It's gonna look at this position, this position, this position, and then it will go to one of them. So then it will go here, and then it will try searching if there's any other positions, but then it will be like, no, I already looked at these 2. Then it will go here, then it's gonna see this position, and then it'll be like, okay, I'm gonna go back, I'm gonna look at this one, and then when it goes to this one, it's gonna be like, oh, there's nothing available except this one, which I already checked. And so then it moves to here, or like, yeah, it moves to here, then checks the positions from here, and so on and so forth. You see how it connects. And then depth first search here would go ahead and just go down one path. So it's gonna go down here first and be like, all right, I'm gonna go here. Oh, there, it's connected with this. I'm gonna go here. This is connected with this. I'm gonna go here. Oh, I can't move anywhere from here. Wait, I can. I'm gonna go here. All right, I'm gonna go here now. And then it will see the finish line and be like, yippee, it's solvable. Alright, now to explain the code. So, I'm going to go ahead and explain. I'm going to explain all of this later because they're important, but for now, you just want to make a maze initializer. My constructor only consists of declaring the column and row size. It also consists of making seconds, because thing is, I'm going to show you right now. So I'm going to go ahead. So as you can see here, I run it by, this is the overall solution I made. I didn't declare this in the beginning, but I put it that, like, you can see where it's been with putting the word C on it, marking it as, oh, like the thing has already been here, just so it's not as confusing. So you can see where it's been overall. And so that's where the seconds comes in, because you see how it kept on clearing, but like it looked like it came in from frames. And that's the whole thing. It basically runs on a bunch of frames, so it looks continuous. You could make it that it goes down with a bunch of mazes, but that's kind of ugly, so I decided to make it frames per second. So every frame in whatever second declared, system clears the terminal and then shows the maze, as you can see here. So that's what this is all about, and the row size and column size is pretty self-explanatory. Now we go to initialize. Now you can, it may be, someone may question me on this and say, oh, why the hell do you not put the initialize in the maze? Like why would you not put this in the constructor? And to that I say, because I'm stupid, alright? That is smarter, but when programming this project, I just did this so that I call maze.initialize in the main CPP. Dude, I don't like saying that. It initializes the object string right here. This object vector, it initializes it. So it puts all the objects, like I told you before, where we're going to essentially store the position of a bunch of objects and obstacles, and that's how we're going to know where the X's, the O, and everything is at. And so when you initialize here, all this is doing is essentially providing the dashes. This is for like the upper row and the bottom row. That's what this does. And then other than that, it then provides the walls on the side. This is what this does. And then it does whether or not a space is going to be an O or an X. Here, like it's randomized, and it looks like I made it a... No, I didn't make it a 50-50. I made it a 33-66%. So 33% is an X, 66% is a space. You can make it whatever you want. I did this so that most of the maze is solvable, like most of the randomly generated mazes are solvable. I don't know how that works mathematically. I didn't do the mathematics, alright? I'm lazy. I don't want to do it. Someone in the comments below can do it. That's much smarter than me. Anyways, so, and then I declare the initial player position, which is the corner, and then the flag position, which is over on the bottom corner. You could go ahead and change this stuff, by the way, if you want. I just gave you the basic specs, but go ahead and play around with the project. I'm sure you'll learn a lot like that. I mean, I didn't play around with it because I spent 3 hours on this. And then void display, this is just a for loop on the object, so that you just display every column. Like for every column you just display, whoa, for every column. Wouldn't it be every row? It should be row size and then column size based on how the vector is, because you go through the rows first, the rows being the strings, and then you go through the column size in order to fit out the string. It's a basic logic mistake. Watch out for that if you have that in your code. I don't think I'm the only person that does that type of stuff. Anyways, so that's how you generate it, and this is how you display it. The solutions here, let me go ahead and just full screen this. For the solutions, we have breadth first search and depth first search. Now, in order to program a breadth first search, you use two data structures. Well, you do a lot of data structures, but like you can see I have a lot of data structures, but here, the most important thing with breadth first search is two data structures, queue and unordered map. A queue is a data structure that is first in, first out. So when you put something in a queue, you only get the first thing that came in, and then when you pop it, it's the first thing that came out. It's basically an array, but very like strict with its ruling, right? And then we have an unordered map, which an unordered map is essentially something that, for the sake of the video, an unordered map is just something that allows us to grab a key in O of one time based on how it hashes things. So it when you call an unordered map with a key inside of it, like here, you see that there's the key right here. And when you call an unordered map to check if it contains a certain key, it will go in of one time because it just hashes and then checks if this hash exists. I mean, it's much more complicated than that, and that's for an unordered map. An ordered map is of log of n. And I'm going to explain more about maps in another video. Leave a like if you want me to. Okay. So here, essentially, we're going to do the same logic that we had, that I showed you. The same logic that I showed you in the pre-recording of this was right there, in that you use a queue in order to find out, oh, like, what are the things nearest to this? And then you go back and then you check what is the things nearest to this other node. And that's what we do with the queue here. So essentially the logic is, while the queue isn't empty, so obviously, well, we still have things in the queue, like there's still places to explore. We go ahead, this is for framing, the auto start and all that, that's for framing. Because here I do the frames here, so whenever the thing moves, it restarts in the display again. And this is tracking, by the way. This is what you saw earlier. I made it into a Boolean value so that if you wanted to not have tracking in the main CPP, you can just put false. I'm gonna go ahead and normalize it to true for the most part, but you can turn it false if you want. You go then get the front value. So we need to first put the player position. This is our first starting point. Obviously, this is going to be the head of the tree that I showed you. And so then you pop it, you remove it so that you don't redo the duplicate. And then you go ahead and this is for displaying. So you pop it and then you put the player position here. Obviously, for the first one, we don't need to do that since the first one's going to be 1-1, but it's for later on. And then here, we check all 8 positions nearest to us. And then from those 8 positions, then we go ahead and check if one of them is the finished position. If it is the finished position, we could just go ahead and finish right there. Like, we could just go ahead and finish the simulation, as there's no point of checking any other path. And if we didn't find something that was the finished position, we go ahead and then see whether or not what we're looking at is a space, something we're allowed to go onto, and whether or not we've already gone to there. That's why the unordered map is important, because we basically store all the positions we've been at, and then we check from there whether or not we've seen that position. And so if we did see that position, we're not going to obviously put it back into the queue because it's a waste of time. And then here we go ahead and push it in the queue and put it in our history. And then here's all the framing stuff. This is not so important. You don't need to do this. And if you want to do this, there's a lot of articles online in Stack Overflow, questions that you can search up that tells you how to do framing per second. This is not even the most efficient method, so you guys could explore that if you want to. It's a pretty cool thing. Now, depth first search is the exact same thing here, but the main difference between depth first search and breadth first search is the data structure, which I use stack here, which is last in first out. You see how everything connects? How in the recording I had, how breadth first search somehow is able to go through like all of the possibilities and then continue on after. But depth first search is the exact opposite because it uses stack. And so it won't go through all the possibilities. It's going to be last in first out. So it's going to look at the last thing you put. So if you have a tree, it's going to put in the last thing, the last node. So essentially that's the difference between the two. Just one's on stack. If you could visualize it, back in the example, if we go on our stack and we go from right to left, obviously the left one is going to be the last one. And so then that last one, we check on that last one, and then we go down that path, right to left, and then we see, okay, we're going to go down left again. And if there's no nodes to connect to, then we will not go down. And then we'll go back to our previous checkpoint. And that's how last in, first out goes. It's really cool stuff. And outside of that, it's the exact same logic as breadth first search. It's just instead here you have to put the stack at the bottom here. You need to do the s.top and s.pop here instead of breadth first search where you do it at the top. This is just more of a logistic issue so that the data structure doesn't get messed up. And that's the entirety of the project. Hit a like, subscribe if you liked it. If you didn't like it, dislike it. Hopefully tell me why you dislike it.